Well, good morning, everyone. Thanks for joining me. How are we all feeling today? Week 2.
Pretty good. How are you feeling, Professor?
Doing well. Thanks for asking, Charles. Before we get started today, I wanted to see if you guys wouldn't mind introducing somebody to you. And he's one of my all-stars that I recruited. His name is Anthony. There he is, the man, the myth, the legend. And I recruited him last semester. He's been with me for about a year now in these weird online settings, but he's been an all-star regardless of the setting, and he really understands the material. He's a hard worker, and he's just an all-around good dude. And so I was able to get him to be, just for our class, our TA. So he's going to be helping out throughout the semester. He's going to be there just for you guys in the tutorial center. So I just wanted him to come, show his face, say some words so that you guys know who he is, where you could find him, and hopefully you saw his message go out yesterday about availability and trying to see what would work best for those of you that would actually take advantage. All right. So Anthony, if you want to say a few things, just introduce yourself and let the people know where they can meet with you and all that stuff.
Yeah, so my name is Anthony, of course. I'm gonna be your embedded tutor this semester, and I've been working in Mr. Allen's class for like the past year now. I took the same class that you guys are taking now last semester. So I know it might seem a challenge, but I'll be here to help you, and you can like find me at the tutorial center. I'll have a Zoom link for you guys once I figure out my schedule. So I'll send a message out with that. I did send a message out in Canvas with a poll I'd like you guys to take. I saw a few of you did already, which is good. But once I have my schedule ready, I'll send out a Zoom link for you guys to join up, and you'll be able to meet with me at set times. And other than that, you can utilize just the regular tutorial center hours if you need some extra help. I believe their hours online are from like 10 to 9 p.m. Throughout the week. But yeah, so, I guess just a little bit about myself. I'm a student just like you guys. I'm working towards transferring. I'm majoring in computer engineering right now. And so, yeah, going through my math sequence and stuff. So I know math can be a bit of a challenge, but hopefully, yeah, me or Mr. Allen can like help kind of mitigate some of that challenge. Anyway, yeah, that's about it. I look
Perfect.
forward to working with you all.
Awesome. Thanks, Anthony. Anybody have any quick questions for him while we have him here? All right, great. Well, again, I just wanted him to pop in now that we kind of got his availability figured out. And again, since this is a 100% online course, he will be 100% online as well. Like you said, he'll send out the Zoom link so that you know what days, times, and where to be able to meet with him, hopefully in small groups, work on your group quiz, homework, whatever it might be, any concept that you're struggling with. Okay, awesome. Thanks, Anthony. All right, guys, just a little bit about today, what we got planned. Now, remember, we normally meet Monday and Wednesday because of the holiday on Monday. We're meeting today, obviously, because it's still a Wednesday, but I'm also going to meet with anyone that can on Friday at 9 a.m. as well. Normally, I have office hours during that time, but I wanted to keep it consistent with our meeting time. Okay. Today, we're actually going to get started on trig finally. But before we do, I wanted to make sure that you guys had an opportunity to ask questions, check how you did on that group quiz 1, which was all basically prerequisite knowledge. And then at the end, those last 2 pages, I really challenged you a little bit more. If you struggle with those, no worries. I'll grade that part a little bit easier. Okay. As long as you tried it, that's all that matters to me. All right. So I'm going to give you guys an opportunity right now to look at the answer key. So if you have your group quiz handy, great. If you don't have group quiz 1 handy, go grab it real quick. and I will put up the answer key for you to pull out and check. And then we will go ahead and go over anything that you guys have questions on for this first hour or so. Okay? So let me pull that up for you. And hopefully you guys can see all of that there. Can everyone see that okay? Somebody put in the chat, the last 2 pages killed them. Yeah, those were tough. Those were challenging. Those are some of the things that I'll definitely go over. A few of you are agreeing. So go ahead and take some time. I'll go ahead and pause the recording, but take some time to check your answers, circle any that you want to go over, and we will go page by page through it. And I'll go ahead and give you the opportunity to ask questions with me, or I'll even throw a breakout room and you can ask other questions to Anthony. Okay? So I'll go ahead and pause the recording for now. All right, now that everyone's back, wanted to quickly go over some of the stuff that you guys were struggling with before we actually start in on our trig today. So if you guys are cool with it, we'll go page by page and you guys just fire away and let me know what kind of questions you would like to get a little bit more clarification on. And then we'll take a quick break at the end of that, and then we will start in on the very first section of trig 1.1. And whatever time is remaining, you guys will have time to work on that first group quiz I labeled 2.1. Week 2, first meeting. The other one will be 2.2, and that will be on the next 2 sections that we will be covering. All right, and if there's nothing that you guys want to cover on a certain page, even better. That's a good thing. And you can speak up or say it in the chat. All right, so let's start on page 1. Anything that you guys want to cover, numbers 1 through 8. Got it, Jacob, for sure. Nothing on the first page. Excellent. How about the second page, 9 through 14? All right. About 15 through 20 on that third page. Anything 15 through 20. Important stuff there. Make sure that you know how to factor. Samara, thank you for answering. All right, we'll go to page 4, 21 through 29. Anything 21 through 29. Cool, feeling good. All right, we'll keep rolling. Maybe I should have just asked you guys which ones you want to go over. We're almost there though. Page 5, 30 through 37. Anything there, 30 through 37. Oh, let me backtrack. I missed something. Somebody said 28. All right, let's go over 28. So we got x squared plus 4x minus 21 equals 0. And we're in an equation. Remember, an equation is one of those 3 most important things I told you at the beginning of class that are the most important concepts in all of math. And when we have an equation, that means that this side is equal to this side. We just have to tell them for what values of x would make this a true statement. So we should know that by the degree, the highest exponent of this equation, there are 2 possible answers. And the way that we like to solve when there is 1, 2, three terms, we call it a trinomial, is by what? It's called factoring. Okay, and in order to factor this, we're going to undo, we call it the inverse, we're going to undo our distributing. That's what factoring is. Okay, and I know if I'm going to put something in the first two slots, when I distribute that, I would get the first thing. And when I put something in the last two slots, when I distribute those, I'd have to get the last thing. The hard part is when we do the other distributions, that's how we get the middle. And you guys know how to distribute. Hopefully you know how to factor. I know the only way to get x squared is by putting an x there and an x there. I know there are a few different ways to get 21 though. 1 in itself, 3 and 7, and that's it. Now, most of the time, it's not going to be 1 in itself. It will be the other pairs, however many there are. Doesn't mean it can't be that, but most of the time it is not. So I'm going to guess that a 3 and a 7 go in one of these two slots. Now, does it matter where I put those? No, not on this one. Go ahead, Samar.
When we do it though, the 7, oh wait, hold on. Oh yeah, the 7 has to be positive, right?
Okay, very good. It doesn't matter where we put the 3 and the 7, but it does matter what sign we put in front of them. Because I know that these things multiply to 21, but it has to be a negative 21. And the only way that we can multiply to get a negative is if one is positive and one is negative. But this could be negative and that positive, and it still gives me the negative 21. So like Samara said, what we have to make sure of is that we get that middle, that positive 4x. And since my signs have to be different, I look to the middle to see what my bigger number has to take on. What sign? Very good. Excellent, Samara. So that means I'm going to have a positive with the 7, a negative with the 3. And now all we're going to do is check. And what we really don't have to do is check the first and the last. Because if it doesn't FOIL out to multiply to those things with this factoring, then you shouldn't have even put them in there, right? We know this times this is going to give us that. We know this times this is going to give us that. The only thing we really need to check is the x and the 7, which gives us positive 7x, and the negative 3 in the x to give us that 4x in the middle. Very good. We factored just like we did in some of the previous problems. But remember, this is not just a factoring problem. It's an equation where we're trying to see where it's equal to 0. We didn't know what squared plus 4 times what minus 21 gave us 0. But now look what we have. Don't even worry about the insides right now. We have something times something. And when is something times something going to equal 0?
When it's times 0.
Good, very good. Only when either this or that factor is equal to 0. That's why we have to get it to be something times something equals 0. And now we have the factors. And just think about it. What minus 3 would give you a 0?
Three.
And what minus or plus, excuse me, what plus 7 would give you 0?
Negative 7.
Then those are our two and only two solutions, answers, things that would make that equal to 0. Okay, so just applying the factoring. Now, again, I'm cool with you guys just jumping to these. If you want to go off to the side and say, I know x minus 3 has to equal 0 and x plus 7 has to equal 0, and then solve that, that's fine too. You'll see that you'll get your 3, and to zero that out, a -7. But whenever you have a single x plus or minus something, it will always be the opposite to get back to 0. If there's a number in front, like a 4 or a 2, changes things. Because now you're not only going to have to add the 3 over to get rid of that, you're also going to have to end up dividing by that thing as well. Okay? Pretty simple. Be careful with it. Good question. Anything else on page 5 now, 30 through 37 that you guys would like to go over? $37, you got it. Another similar one to the one that you guys started doing with Anthony in the breakout room. 37 says a wheel moves at a rate. There's a key word, a rate of 270 revolutions per minute. Any car people out there? $270 revolutions per minute. That's the rate that we are traveling at, they said. Now, that's a lot to say, and we can minimize that by just saying 270 RPMs. That's why I asked about any car people out there. You are familiar with a rate of miles per hour, but this is actually how it's set up. Because you guys may remember that distance is equal to rate times time. And if you want to know just the rate, then you would have to divide both sides of this equation by time to figure out what the rate is. And notice it is a distance over a time, that ratio. This is the distance that we're revolving around, and this is the time that we're doing it in. This is how we say it for short. Miles per hour, RPMs. Okay, what we have with that though is a question that they want us to answer. Through how many degrees will a point on the edge of a wheel move in 5 seconds? How many degrees in 5 seconds? So we obviously have a rate here, and we also are given a what there?
The time.
Very good, Samara. Then if we have a rate and a time, then what should we be able to find?
Oh, we can find the distance.
Very good. Because we know that distance is rate times time. All we have to figure out is what the rate is and what the time is. And remember, they wanted it in degrees. So here's our setup. All we have to do is plug in what we were given, and that was 270 revolutions per minute. I'm actually going to write it as a ratio and not the condensed form. And then I'm going to multiply it times the time, which was in 5 seconds. But there's a few problems with this, right? They wanted to know how many degrees does a point on a wheel rotate around in 5 seconds if it's traveling at this speed, 270 RPMs. Well, notice that this, my rate was given in minutes, and then they told us in seconds for that tire rotation. So if you guys remember, one of the most important things I told you in all of math is multiplying by 1. Okay, you will do this again and again and again, not just in this class, but others as well. So by taking anything and multiplying it by 1, I'll get the same thing out. It just may be a different looking one. Right? We may just want it to be this instead of the original thing that we started with. So what is the one that I want right now? Well, I don't like the fact that I have 2 different times measurements, seconds and minutes. So what I'm going to do is I'm going to put the seconds on bottom here so that these will cancel. And then I'm going to put the minutes up here so that these will cancel. But do I know a direct relationship between seconds and minutes?
60 seconds for 1.
Very good. Then if we know that 60 seconds is equal to 1 minute, and I want the minutes on top and the seconds on bottom, then I can actually take and divide. I can do whatever I want to an equation. So if I want to divide both sides by 60 seconds, then I know that this all cancels out to be a 1. So we know that this is equivalent to a fancy 1. Then that's what I'm going to put in here. We know that 1 minute divided by 60 seconds is just a fancy 1. But why are we doing that? What happens? Anything divided by itself is a 1. So these minutes and those seconds will cancel out. And if you want to divide the 5 into the 60, you can do that, or the 60 into the 270, you can start doing all of that, but I'm going to just hold off on that until the end. And where is the end? Well, remember, we're trying to find how many degrees in that 5-second time at that rate of 270 RPMs. I need to change to degrees. Notice all of my units have canceled out except the revolutions. So unfortunately, gang, we're going to have to multiply by another fancy 1. And we want to get rid of what? We want to get rid of the revolutions and change it to degrees, because that's what they asked for. And because the revolutions are on top of this whole fraction, I'm going to put it on bottom so that it will cancel out. So I'm going to put revolutions down here. And what do I want to change it to?
Degrees.
Do we know a direct relationship between a revolution and degrees?
No.
All right, Samara, think about it. If I was to make 1 revolution all the way around, do you know how many degrees I would?
Oh, 360.
Yeah, very good.
Yeah.
Again, we haven't even gotten into trig yet, but I'm trying to show you guys this is stuff that you can do already. Because very good, we do know if we started here and went all the way around 1 revolution, we would have traveled a different measurement, 360 degrees. And that allows me once more to cancel the revolutions, the units I did not want, just like the minutes and seconds. And notice the only units that are still there are the units that they asked for. So the only thing left to do is multiply everything on top and bottom, and then see what's left. Now, if you wanted to, you could also start canceling anything on bottom with anything on top. So for us, that would mean I know that 60 goes into 360 6 times. And then I would have 6 times 5, which is 30, times the 270. Which I recognize this as a 3 times 10. And I recognize this as a 27 times 10. And I know 3 times 27 is 81. And I know 10 times 10 is 100. So it's 8100 degrees. That's how many times we would rotate around in 5 seconds if we were traveling at that rate. Okay, kind of cool that we could figure that out by just multiplying by 1 2 times. Okay, great question. A couple of you asked for that one. Let's get to the last few pages that many of you were asking about. Let's look at 38 through 41. And again, you guys already started in on 38, so let's do that one. And then I'll open it up to any others on that page, which should have been a little bit easier. Maybe 41, you might need some help on. This one's really cool. I'll try to not elaborate too much, but again, what is the very first thing it asks?
How long?
Which means, what are they asking for?
Time.
Good. Now that could be a distance as well, but you've already read and tried the problems tomorrow. Very good. How long would you have to swing a bat if the pitcher you're facing throws 90 miles an hour? So very good. We want to know a time after how long a pitcher has thrown a ball at a rate of 90 miles per hour. I'll rewrite that in its fraction ratio form in a minute, which means if we have a rate and a time, what else would we like to know?
The distance?
Very good, Tamara. Distance. Now, I did have to give you that one because that's something that not a lot of people know. The distance in professional baseball is 60 feet, 6 inches from the pitcher's mound to home plate. So again, we know that distance is equal to rate times time. And since we're trying to find the time, we're going to divide both sides by r. So to find our time, we need to know the distance over the rate. And we know the distance is 60.5 feet. Everybody okay with me putting 60.5? We know 6 inches is half of another foot. So 60.5. And then our rate, I'm going to rewrite that as well as 90 miles per hour. And there's our answer. We have everything we need to find the time. The problem is, this is a nasty mess, isn't it? We got fractions within our big fraction. We don't like that. We don't like to divide by fractions, so guess what we're going to do? Anybody?
Apply by a fancy one.
You got it. You're starting to get the hang of it. Samara, I'm so glad you're here. Thanks for talking. Doing well. Now, the one that is fancy is going to be what is called the reciprocal of the denominator. So we're just going to flip what we had here to get this, which means if I do that in the denominator of my fraction, I have to do it in the numerator as well. And notice what's going to end up happening is all of that becomes a 1 and all of that becomes a 1. So now we can forget about that because it's just all dividing by a 1 now. So what's left is 60.5 feet here, and it was being multiplied by the 1 hour divided by the 90 miles. And hopefully you guys remember from the other day when we were doing some beginning sample problems, what are we going to have to do in order for this to make sense for what they asked?
We have to get rid of the distance measurements, right?
How?
By multiplying by a fancy one again.
I'm trying to get you guys to understand how important and how easy it is to do. Now, Samar, the hard part about that 1 is figuring out what that 1 is, right? You know you're going to have to manipulate this, changing the units. We call it dimensional analysis, right? But I want to get rid of the feet and the miles to make a little bit more sense. You don't have those in time. Hey, how long did it take you to pass Math 4A? Oh, you know, it was like 3 feet months. What? We don't have distances within our time. So we want to get rid of those. So what do I want to have up here and what do I want to have down there in order to make this sound and look a little bit better?
Minutes and feet.
Good. Now remember that does not stand for minutes, it's for miles. And we want to put the miles on top. Very good, Eric. And the feet on bottom. Again, how come?
So they can cancel.
Excellent.
Reciprocal.
Not just the reciprocal, but I see what you mean. Because the feet will then cancel out because one's on top, one's on bottom, and the miles will cancel out. But do you guys know how many feet are in 1 mile?
5,280.
Good, very good, Eric. Do you guys remember me going over that?
Yeah.
We proved why it's 5,280. And again, this is our system. I'm hoping that you guys would know it. So by doing that, we're able to cancel the feet and the miles to now just be left in hours. But have you ever watched a baseball game or played baseball and somebody throws 90 miles an hour? You guys know, you've been in a vehicle. That's fast. Are you sitting there for hours waiting for that 60.5 feet that they were throwing the ball? Are you waiting for hours for it to get there?
No.
So that doesn't, even though it's time, that unit measurement doesn't really make sense either, does it? So guess what? We're going to multiply by another 1. To get rid of the hours, which is on top, I'll put it on bottom. And what do I want to convert that to? Seconds actually makes more sense, but I don't know how many seconds are in an hour. I know there are 60 minutes in an hour. And that now allows me to cancel the hours. But again, you're not sitting there waiting minutes on minutes for that pitcher throwing 90 miles an hour, 60.5 feet to get there. So unfortunately, we're going to multiply once more by a fancy 1 to get rid of our minutes and change it to what does make sense, and that's seconds. And we know again, 1 minute is equivalent to 60 seconds. And by the way, guys, if you know this, that's something that we're going to learn this week as well, but in trig form, measuring angles. We're going to use those conversions. So finally, we've canceled all the units but seconds. Now all we have to do is multiply all the stuff on top and all the stuff on bottom and divide them. And you guys saw the answer key. We get a time of approximately 0.4583 repeating seconds, or about, if we were to round, you have about a half a second until the ball is going to be across the plate, which means you actually have even less time to decide to swing to hit that ball, which is why some of these people get paid millions of dollars, because that's not easy, especially when they're throwing curveballs and changing the spot around. Not to mention it's a round ball with a round bat that you're trying to hit. Not easy. But what ultimately did we do to solve that problem? We multiplied by 1 3 different times to get our time by manipulating the distance formula. Do I expect you guys to get that on your own? No, that's why I let you work in groups, so that hopefully you can try to manipulate and figure some things out. But even still, that was a pretty challenging problem. All right. Anthony didn't get that one last semester, so that's why I didn't give him this problem. That's why he didn't really know where to start on that one. But start with what you know and what you don't know. And if you can come up with an equation with those things in it, then hopefully you know how to solve it. And that's ultimately what we did. It's a good rule in all of math. Take things they gave you, figure out what they want to know, see if you can put those into an equation, and then solve it using all of your previous algebra experience. Okay. Great questions. Anything else up through 41 on this group quiz? All right, then let's move on to the last page, 42 through 45. Anything 42 through 45? All right, 44 and 45. I figured those two. Okay, great. 44 is a trig problem. Some of these other ones are related, but not directly what we'll be doing with trig. This is something that we will do and see soon. 44 says if a tree 27.5 feet tall casts a shadow that is 11 feet long, find the height of a tree casting a shadow that is 13 feet long. So we got a tree. We got the sun. And we have a shadow. Now, before I draw that, this is where a lot of people screw up. If you are going to look at your shadow, where are you looking?
You're looking in front of you?
Very good. Where, Samar?
Forward?
Good. So is it this?
Oh, I
You said
see.
looking forward. Is that going to
Yeah.
be your actual shadow?
Your shadow's like gonna be from the floor coming out.
Very good, Peter Pan. I mean, Samara, right? That's the mistake that a lot of people make, is they'll say that this is the shadow, when in reality, your shadow is going to be on the ground, not this part. But guys, don't forget, what class is this? Don't say Math 4A, but what is it actually called?
Trigonometry.
Which is the geometry of what?
Triangles.
Triangles.
In what triangles do we prefer?
Right triangles.
Right triangle.
Right, you are. Very good, Charles, Samara. Guys, we're going to be drawing a lot of triangles in this class. And if you don't know what to do, think about trying to draw a triangle. And what do we hope it is? We hope it's a right triangle, because then we can use all different kinds of things, like the trig that we're going to introduce here pretty soon. Sine, cosine, tangent. The Pythagorean theorem. Some of the things that you guys remember, hopefully, from geometry. But again, it's been a while. That's why we're starting this class off nice and slow. All right. Now, it doesn't matter that you get out your shade sticks and you draw a perfect tree and all. The only thing that's really cool matters is that you label it correctly. You don't even have to draw it correctly. Okay. This opening here for this angle doesn't have to be drawn perfectly. Okay. What am I going to label on this tree correctly? What did it say the height of the tree was?
27.4 feet.
Good. And we know that this is the height of it. But as I mentioned, and Samara figured out, along with Charles, that bottom is going to be the shadow. And they said that that was 11 feet. So again, does this look to scale? No,
Yeah.
doesn't have to. That's the beauty. The mathematics will take care of itself. This should definitely be a lot taller than that. Over twice as tall. But as long as I have it drawn like this, it's all good. Now remember, it said there was another tree and another shadow involved, which means another right triangle. Now let's make sure we label this correctly. What did it say?
The shadow is 13 feet long.
Then we know the shadow is down here, and we know that they want us to find the height. Whether you call it X or H for the height, totally up to you. And because it's from the same time of day, near each other, we know that these two triangles, are they the same?
They're similar.
Very good. Definitely not the same, but they are similar. Because they are both right triangles, because most trees are straight up and down, then I know, because the sun is the same, that this angle would be the same as that angle, and therefore this angle would be the same as this angle. So they are what are called similar, but not the same. And because this is bigger than that, we know that this should be bigger than that. But do you know what similar triangles' side lengths are to one another? They are similar triangles called proportional to one another. So if this was, say, 22 feet, then I would know that this is twice as big as that. And therefore, I could just double this to get that. But it doesn't always work out so nicely. So we need a better way. And all I want to do is find the height of this. I want to find that value. So I'm always going to start with that. And a proportion means that if it's twice as big as something else, then you can set up these two fractions that are proportionate or equal to one another. The cool thing is, as long as you're consistent, it doesn't matter how you set it up. You can do this over that, as long as it's equal to this over that. Or you could do the heights over one another and set them equal, as long as you do this one over that one. the same way you did that. So as long as you're going to set this up, I would always put the X on top and then your choice. Do you want to put it over the other height? Or do you want to put it in the same triangle? Totally up to you. I'm going to just keep it in the same triangle, and I will do the height to shadow ratio. So this over that would be equivalent to this over that. And again, if I wanted to put all the measurements, you could see that these would just cancel out. And what would I do to find the X? If it's being divided, we will multiply. And to keep it equal, I'd have to do it to both sides. Not a fancy one, because it's an equation. I can do whatever I want. If I want to make both sides 13 times bigger, that's fine. It'll still be equal. But because we're dealing with fractions, I'm going to make those fractions so I can see that anything divided by itself is 1. And notice, now I just got a big 1x. All I'd have to do is multiply these things, divide it by that, and that will give me my answer. And you should have gotten a little calculator work, 32.5 feet. Okay, you actually don't even need a calculator if you didn't have one. You can divide 11 into 27. I know it goes in twice. That would be 22, so I'd have a 5 left over, right? And then bring up that decimal. How many times does 11 go into 55? That's 5 times. So now I have 2.5 times 13, and I know 13 times 2 is 26. And I know half of 13 is what? Sorry, that was weird. I know half of 12 is 6, and half of 1 is a half. Add those together. There's your 32.5. All right. Last one here. Then we'll take a quick break and then come back and start in on 1.1. Right? 45 wanted us to find the area of, I'll try to draw this quickly. All right, my circle with a square inside of it. A little off on my square. And then they wanted us to shade in just the outside of that square that is inscribed in that circle. This is the area we are trying to find. So how are we going to do that? That's a terrible square. Could you tell me what the area of the whole circle would be?
No.
So you don't know how to find the area of a circle. Is that what we?
Pi r
Oh.
squared.
Good. So we know that that is pi r squared. But do we want the whole circle?
No, we want the difference of the areas.
Ah, very good, Eric. That is the key word. We want the difference. We want to subtract off the area of the what?
Of the square.
And do we know how to find the area of a square?
Yes.
It's length times width, or a side squared, because the length and the width are the same in a square. So we, in reality, only need to know two things: the radius of the circle and a side in the square. And they did tell us that these are all a distance of 4, didn't they? So of all of this, pi r squared minus the length and width, what do we know right off the bat? Each side of my square is 4. So I already know the area of that square. The only thing that they did not give you that I challenged you to try to find is what the radius is of our circle. And that requires you to know a little bit of geometry. So remember, the area requires the pi r squared. That's what Eric helped us remember. And that means a radius goes out in any and every direction. All of those are radii or radiuses. Okay, we say radii for plural. So if you notice, what I could do is actually draw a line from corner to corner. We call those diagonals, because that means each one of these are a radius. And do I know the length of any of those things, though? Unfortunately not. If we did, then we'd be done. But what I can draw is I can drop another line called a perpendicular, which allows me to say that I just split this side here in what?
In half?
Which means this distance and that distance would be 2. And if those are 2, then we know that this angle and this angle would have to be the same as well, which means this is 2. And if you know in a right triangle, which we now have here, and we know these two sides, do you guys remember how to find the third?
The Pythagorean theorem.
Very good, Eric. Excellent. I could go off to the side and say 2 squared plus 2 squared equals my radius squared, which is what this distance was, which is 4 plus 4, which is 8. And if we take the square root of both sides to get what r is, then I know that this can be broken down as 4 times 2, and I know the square root of 4 is 2, with a 2 left in. Now I know my radius. And if you got to this part, great. If you're able to do anything else, awesome. Because that's not easy, knowing and figuring some of that other stuff out. Okay, so just kind of wanted to go through that with you all. Challenge you a little bit here on those last 2 pages, but those are the types of things that I wanted to try to get your mind working before we jump into trig. All right, so I'll give you a few minutes. If you need to use the restroom, grab a drink. Hopefully you guys submitted those. I'm going to start grading them today. Other than that, we're going to start in on trig with 1.1 after a short break. Okay. All right, welcome back. 1.1 is what we're going to start the class with. This is the very first section. All right. Now, remember, most days we'll have the beginning to kind of go over any homework, group quiz questions that you might have. Give you guys like 10, 15 minutes tops. Then we'll go over a section like we're going to do now. And then we'll pause and let you guys work on the group quiz portion for that section. Then we'll stop, do another section of quick lecture, and then the rest of the remaining time will be for you guys to finish the group quiz on those two sections covered that day. Okay. And we can obviously tweak that if you guys want to just do lecture, quick break, and then lecture, and then have the rest of the time to just do the group quiz. We can do that as well. Just talk to me. I'm good with adapting whatever works best for you guys. Okay. 1.1, angles. Before we can get to 3 angles or triangles, we got to start with the initial measurement of an angle. And where I'm going to start you is with a little thing called the number line. And on the number line, when you first started learning it, what's the most important thing about the number line?
It's infinite, negative and positive.
Okay, very good, Eric. You're getting to the point that I'm trying to get you to say. That is the thing that separates those infinite positive and infinite negative values. Very good. So when we started counting, we started going to the right and we learned about numbers in general. And then when we got better, we learned that, hey, you know what? There's another side to numbers, which unfortunately most of us know, and that is debt, right? And that is the negative side of things. Okay, but there is that one value that separates the positives and the negatives, and that is the number 0. Once we learned that in depth, the number line, we added another. And once we added another, we said, well, the 0 is what split the positives and the negatives when we just had the number line by itself. Well, when we add another one, then that's also going to split those infinite number of positives and negatives, but in a different direction. And we called that the X and Y axes. Still splitting the positives and negatives, but this time in all directions, left and right and up and down. Okay, so when we talk about measuring an angle, we know we need a couple of things, right? What would we need if we wanted to, say, plot a point on that X and Y rectangular or Cartesian coordinate plane? How would you get to that point P? If I was stranded out in the wilderness, like Samara's picture, that's all I saw were trees and stars, and I had no idea. But I mapped myself, and I knew from where we started, we call it the origin, where we originated from. I ended up here at this point P. Well, if I had my X and Y axes labeled, I could tell you to march right so much in the X direction, and then up so much in the Y direction. And that's how we label points typically. We'll learn different ways of doing that in this class. Okay, but if I wanted to get to that point from the origin, I would go right some X, up some Y, and notice, what are you already wanting to do? because this is trig, you're probably wanting to say, you know what, this is a right angle. And if I just connected those points where I originated from and where I ended up, point P, I can form a, not just a triangle, but a right triangle. So how else, rather than just saying march X and up Y, could I get you to get and rescue me at that point P? Well, I know you can go up and over some Y and some X, but remember we started with the number line. So that's why we usually do X first. Then we'll do the other one that we added on, which is the Y second. Alphabetical, the way that we learned. But does anybody have a quicker way that you might be able to get me to that point from our starting point? Any ideas out there?
Would it be a different coordinate plane? Maybe Z?
Okay, how would you get me there if you just added a new letter like Z?
Just like the red line diagonally.
Okay, very good. Now I'm going to actually call it R, and you're going to see why in just a second, Eric. But very good. Now, if I told you the distance of R, say it was 5 miles, I was 5 miles out. How would you know to walk in this direction 5 miles to get there? Wouldn't you just walk out 5 there, or 5 there, or 5 there?
By the degree of the angle.
Very good. Now, remember, we said that we're always going to be starting in the positive X direction because that's where we started learning numbers, was on the number line in the positive direction. Then we learned about negatives. And when we got good at that, then we added a whole nother number line called that vertical Y-axis. So if I wanted you to get there faster, rather than walking over 3 and then up 4 for a total of, say, 7 miles, couldn't you just walk 5 miles in that direction? But as Eric mentioned, I'm going to have to tell you, you know what? Start looking at the positive X direction where we originated all of our counting and learning, but rotate some angle. We're going to call it theta, just a Greek letter. It's like a 0 with the line through it. That's what we use to represent unknown angle measurements. Okay, theta. If I told you to rotate 45 degrees and then walk out 5 miles, wouldn't that be faster than going 3 and then 4? So those are alternative ways that we will eventually learn how to get to different places. Okay, and it's not just over here. We could be in any one of these, or even on one of our 4 quadrants. Okay, those are all things that we're going to talk about. Now, lastly, before we move on, what if I wanted to tell you that distance R, but I wanted you to rotate that distance in any direction? What would happen if I just kept rotating around that 360 degrees? What would I form? Hopefully you can see my circle, which is why instead of using a very good point that Eric made was, well, this is X, this is Y, let's just use Z. We're going to actually use R because we're going to be dealing with those rotations of angles and those distances, which would therefore be what is called a radius of a circle. Okay, so later on down the road, we'll actually get to a point by rotating some angle theta and walking out some radius length r. Okay, this is what you know. This is where we'll go. Okay, that's pretty much it as far as the introduction of 1.1. Now we want to make sure, since it was titled angles, that we actually know how to classify angles. That means we need to know all of their names and why we call them that. What are their attributes? So some of the things that you guys may be familiar with, we want to make sure that we know what a positive versus a negative rotation or angle is. You guys probably remember acute, right, obtuse, straight angles. There's also quadrantal, coterminal, complementary, supplementary, and then we'll even talk about how to get an even more precise measurement of an angle than just degrees. Okay, excuse me. So all we're going to do very quickly is define all of these things. So this would be a good thing to do, is take notes on this. All right, and you can look up the more formal definitions if you want, but all I care is that you understand and can use these. So what do you think a positive angle or rotation would mean? Versus a negative rotation or angle. What do we say we would always start by looking? Down our positive right, because of the number line. And if we're going to rotate for an angle measurement in the positive direction, do you think that's up or do you think that's down?
Up.
Very good. Why?
I think it's up because I thought of it like as in slope that way, because when you go up, it's positive, and when down, you make the slope negative.
Exactly. Just like we talked about here. Positive, positive. We're going to start in the positive direction always. And then we're going to rotate if it says positive up. Where we would rotate down if it's negative. But we, unless they say otherwise, are always going to start by looking in the positive X direction of our number line. So that's what we mean by a positive rotation of an angle. Now, you guys know that if I go all the way around, I've rotated what?
360 degrees.
Very good. We know all the way around is 360 degrees. That's what we cut up a circle into, is 360 little parts. So when we say a positive, that means you're going to start up from the x-axis and go around however much they tell you. Or you could go what?
Down.
Which would be a what kind of rotation?
A negative rotation.
Very good. So positive versus negative. Always from the x-axis. Either up or down. Okay, always starting where? In our positive number line on the x-axis. All right, so now that we've talked about the rotation of positive versus negative angles, let's talk about some more precise angles like acute, right, obtuse, straight. You guys familiar with those?
Yeah.
Good, then help me out. What is what?
An acute angle,
Yep,
it has to be less than 90, right?
very good. So when we start rotating, we get to a milestone at that 90 degrees. And every one of these is going to be 90 degrees. That's why we draw these right angles in, and notice it forms a square. Okay, so 90 times 4 is that 360 that we said would go all the way around. So we virtually just cut this into fourths, which is why we got 9 and then 0. 90 degrees for each one of those. So an acute angle is anything before we get to that right angle we call 90 degrees. So very good. Acute angles are any angles that are less than 90 but greater than 0. Obviously, a right angle is what?
90 degrees.
When it's exactly and only 90. But what if we kept going? Instead of from there and anything in here, that's acute. If we get right there, it's 90. What if we keep going into that second quadrant here? What is
Obtuse?
anything over here going to be? Very good. Obtuse, which means it's bigger than 90, but less than the next 90, which the next 90 would be all the way to here. And guess what we call that when we get all the way here, if we started here? What kind of angle?
Straight angle.
Very good, Eric. That means exactly 180. Now that's where we actually stop. And why do we stop there for classifying these things? Because if I go any further past that, I'm going this direction, right? Let's say I go 270 degrees all the way to here. What would have been faster than going 270 degrees to get to this point?
Going the other way?
Instead of going positive 270 degrees to get here, very good. Samara, what could I do?
You could go the other way, so the negative way?
Negative how much?
It was, is it 90?
It is indeed, because it's on my quadrant. So what would you rather go? All the way over here, 270 degrees, or just go negative 90 to get there? Because they're equal, it's the same point. So that's why we stop once we've gone all the way to the opposite side. Because anything more than that, we could have just gone negative to get there faster. Because that's less than 180 in the negative direction. Does that make sense?
Yeah.
All right. So notice there are some very key values here. 90 is in 3 of them, and 180 is in 2 of them. Those are very important angles for us. That's the 90 here and the 180 here. .270 would be there, and then we get all the way around from our 0 degree starting point back by going 360 degrees. And since we see and use these so much, we want to talk about what these angles and these together would be. So you guys know that we started with our number line, and then we added another number line, and we called it the X and the Y axis, which ended up cutting it into 1, 2, 3, 4, what we call quadrants. And so any point that lands on one of those, whether it was 90 degrees, 180, 270, or 360, we are therefore going to call those quadrantal angles. So the quadrantal angles are 0, 90, 180, 270, and one full circle back around to the 0, 360. Okay, quadrantal angles land on one of our 4 quadrants. But what is a coterminal angle? You guys heard of that before? Anybody have a loan for either like a car or an apartment or anything like that? You ever heard of a cosigner?
Yes.
A cosigner is somebody that signs the same lease or loan. So co means same. Where terminal is another one that you may have heard, and it's usually an unfortunate thing that you heard, whether it was in the movie or unfortunately in real life with a friend or family member. In a movie, you may have heard of it being called a terminal illness. What do they mean by a terminal illness? That's a sickness that's going to terminate or end your life. Okay, so what do we mean by coterminal angles? Co meaning same, terminal meaning end or ending. So what is a coterminal angle? It's an angle that has the same ending. So if I told you to give me a coterminal angle to 60 degrees, could somebody give me how to get to the same ending point by going something other than 60?
Wouldn't it be just a full rotation of 360?
Ah, very good. Eric, what direction?
In either direction would work.
Good. You can add 360, go the positive up direction. We call that counterclockwise, or you could go the negative direction. Clockwise, and you would get back to that same point. So very good, Eric. What is the key to finding a coterminal angle? Adding or subtracting 360 any number of times you want. Add 360 to that, you're going to be at 420 degrees. Subtract 360 to that, you're going to be at negative 300 degrees. And any one of those 3 things would get you to that exact same point. Okay, so sometimes that's going to benefit us to be able to provide a coterminal or same ending angle, especially when we're given bigger ones than 360. Why go all the way around, starting here, go all the way around and then go 60 more? When I know if I just subtracted 360 from this, I could get to that point a whole lot faster. Okay, very good. Excellent, guys. Those of you that put in the chat, and Eric for speaking up. Almost done. Just a few more, and then we'll wrap it up for today. Have you heard of complementary and supplementary angles?
Yes.
Good. Remember, some of the key values that we talked about and saw a lot were the 90s and 180s, right? Well, then complementary and supplementary angles are plural. That's when we have the sum of angles that equal either 90 degrees or 180. And how are you going to know which one is which? It's very simple. use the values that you know, the 90 and the 180, which is what all of those used for all of our labeling, and use the words that you know, complementary and supplementary, because we know that C comes before S in the alphabet, and we know when we count 90 comes before 180. So complementary angles are the ones that add up to a 90 or right angle, and supplementary angles are the ones that add up to 180 degrees. That straight angle for supplementary. Complementary kind of looks like that right angle. Okay, whatever helps you to imagine and remember these things. Okay, again, hopefully, like Samara said, you already had an inkling of what they were, but I wanted to just submit home and make sure that you do. Here's the last thing that I know hardly any of you, if any of you, have ever seen. More precise ways to measure angles. We already have a circle cut into 360 little slices. That's pretty small, but it may not be small enough. So what we made up were other measurements for these things. And we know that 1 degree is equal to what is called 60 minutes. So if you wanted to take a tiny little slice of the 360 degrees, one of these, if you cut that into 60 little pieces, that would be what we call a minute. So you can see that we're getting to a very, very, very small, minute angle measurement. Okay, more precise ways to measure these angles. But that may not even be small enough, especially for those of you that are getting into the sciences, right? You know that. You guys may have seen war movies before. Have you ever seen a war movie where there's like a sniper with one of those real long guns, and up at the top, they have to click a little thing? Because they may just want to move it just a touch, not a whole degree, but just a touch. Well, that's where they measure it in minutes or seconds. The cool thing is we are already familiar with these measurements. And we know that 1 minute is equivalent to what?
60 seconds.
Nothing changes in degree measurement with the minutes and seconds. It's equal to 60 seconds. And have you guys seen this before? If you have an Apple Watch, go ahead and do a brisk walk and check it out, and you'll see that on there, it'll have these tick marks for your minutes and seconds, right? Use your stopwatch. If you've ever ran track or anything in high school, watch the Olympics. This is what they use so they don't have to write out the words. And in math, we love symbols. Like we made up this weird looking symbol to represent this many things. But as long as we all agreed upon it, then we can not have to do this and just write that. Okay, so this is something that we will be using here and there. Again, pretty simple to know. 60 seconds, we know is equivalent to 1 minute. 60 minutes, we know is equivalent to 1 hour. The only thing that we have to change now is that it's equal to 1 degree. That's the big change. And again, we should be able to rewrite these as fancy ones where we multiply by, say, whatever it is over here by changing it to minutes and seconds, or just writing this and that. because we know that one of these is equivalent to 60 of those. And then we can cancel out the seconds and change it to minutes. Some of the things that we will be doing like we've done in the first week. All right. That is all, my friends. We will go ahead and have a little bit of time to start and work on this group quiz. All right. Hopefully that helps. Otherwise, watch my more detailed videos that I already have on our modules.